Yes, ma'am. Your screen is visible. Yeah.
Can you hear me properly?
Yes, yes. Yes, ma'am.
Good morning, everyone. So today's topic is speech-to-speech translation. I'll be giving you a brief introduction. I would say brief, but actually it is not very brief because speech-to-speech translation technology involves a whole lot of other technologies which I will be familiarizing you with. Okay, so I'll just take you through the entire process of speech-to-speech translation, and in this process, I'll be talking about all the different technologies which are associated with speech-to-speech translation or S2S translation. Okay, so all of you, I'm sure all of you know exactly what a speech-to-speech translation system does. Basically, what you know is that this system has been designed to translate speech in a particular language, say the source language X, to a particular language that is the target language Y. So it is basically a system which will translate speech in one language to speech in another language. Okay, so the basic, the most important application is communication. So I would definitely say most of us have been in a situation where we found it difficult to communicate to a person because we did not know the language in which he or she spoke, right? So I know a particular language which the other person doesn't know, and the other person speaks the language which I do not know. So in that case, it will be difficult to communicate. So a S2S translation tool or technology would definitely be handy in such a scenario, because that would help me bridge the communication gap between the two persons. Now, if I were to define speech-to-speech translation system, I would say it's an advanced system of language translation that translates spoken language from one language to another in real time or near real time. It is expected to operate in real time or near real time. So such tools, that is speech-to-speech translation tools, they rely on machine learning and artificial intelligence technologies, and specifically on NLP, that is natural language processing, ASR, that is automatic speech recognition, and TTS, that is text-to-speech synthesis or speech synthesis. Now, S2ST, I will refer to speech-to-speech translation as S2ST. So S2ST is considered to be a multifaceted problem. A multifaceted problem, a complex and multifaceted problem, mainly because it is intended to function under multiple scenarios, addressing multiple variables. For example, in the figure, you can see that on the one side, these are the different situations under which an S2ST system is intended to function. On the left-hand side, you will see that the constraints are slightly easier, while on the right-hand side, the constraints or scenarios are more difficult. So the S2ST system may be designed to operate offline or in real time, that is simultaneous S2ST system. Again, the S2ST may be designed for a single speaker, that is data from a single speaker, or it can be designed from data from multiple speakers. The input to the S2ST system may be clean audio, or the data may be collected from noisy conditions. Then the system may be designed for resource-rich languages, that is languages which are abundant in the corpus and tools and technologies, etc. Or the system may be designed for under-resourced languages as well. Then again, another facet you would say is the speaker variety. So S2ST systems may be designed for low speaker variety in terms of gender, etc., or it may be designed for high speaker variety. So all these leads to a number of challenges, which you can see are mentioned in the slide. The first is audio challenges. For example, the training data may contain data from multiple speakers. Then it may contain background noise. Then background noise, and then obviously this would lead to issues in audio segmentation. Then another challenge is the text-to-speech mismatch. So if you have to design a speech-to-speech system, there should be a proper match between the text data and the speech data. And if there is some mismatch, then which is obvious, there will obviously be mismatch in text and speech data. For example, speech data may have disfluencies. So whenever I'm speaking, when I'm spontaneously speaking, there will be certain hesitations. For example, I may say, and then there might be repetitions. For example, it had been a good day. So I'm repeating it had, right? Or sometimes there might be corrections. I'm saying something and then I correct and say something else. So then obviously this would lead to text to speech mismatch. So again, text data may be devoid of punctuation. So that would again lead to mismatch with the speech data. So this is a big challenge for S2ST designers. Then another challenge is the error propagation. So mainly in traditional cascade S2ST systems, there will be propagation of errors because the traditional cascade S2ST systems contain three main blocks, that is the ASR, the machine translation, and the text-to-speech module, which are cascaded. And then what will happen? The errors in the ASR will propagate to the next system, that is the machine translation system. The errors there will propagate to the text-to-speech system, and this way the errors will keep on accumulating. Then again, in case of real-time systems, partial information may prove to be a challenge because in real time you need to translate, and the translation process cannot wait till the end of the sentence. You are speaking something, and if you wait for the entire sentence to end, then the processing time that is required, that will not be sufficient to translate the sentence completely in time. So in that case, you should be able to predict what is going to come next. When you're saying something, the system should be able to complete the sentence, should be able to predict the next part of the sentence. Only then it will be able to translate in real time. So why speech-to-speech translation? Why S2ST systems are so important nowadays, and why it is gaining popularity? So as I mentioned, the first important thing would be real-time communication or breaking language barriers, and that is why S2ST systems are considered to be a communication boon, a boon to the communication. Then there are other reasons as well, or other applications as well. For example, S2ST can provide accessibility solutions to people who have hearing and speech impairments, mainly by transcribing and translating the spoken language. And then other applications such as might be used by travel assistants. Then S2ST systems may be used for translating lecture videos or lecture audios, then movie dubbing, language documentation, etc. So I'm not discussing or talking about the technology that has been used in these tools, but I'm simply presenting you some top speech-to-speech translation tools which have been developed by tech giants such as Google, Microsoft, Meta, etc. And which are, most of them are freely available for use. So we have Google Translate, we have Microsoft Translator, then Meta's AI research, speech metrics, Speechify, AI dubbing. There are more, but I have listed some of the most popular translation tools. Now coming to the two basic approaches of speech-to-speech translation. The first approach is the traditional or the classical approach, which is called the traditional cascade approach. So cascade approach, basically three main modules are cascaded. The first module is the speech recognition module. The second is the machine translation module. And the third is the speech synthesis module or the text-to-speech module. The first module, that is the ASR module. Am I audible?
Yes, ma'am.
Yes, ma'am.
So the first module, that is the speech recognition module, the function is to encode the input speech and then transform it into written text. So our input will be speech and the output of this module will be the corresponding text. So this, the entire process involves various tasks. For example, identifying the spoken language, because when the input is given, the first thing will be to identify the language, the language of the input speech. Then understanding the speech in the context of the language. So you have to understand the context also. and then transforming the spoken words into written words. The second module, that is the machine translation module, what will it do? It will translate text in a source language to text in the target language. Okay, so here the algorithms will leverage vast data sets and sophisticated language models will be used to ensure accuracy and fluency. The third and the last module, that is the speech synthesis module. Here, the input will be the text in the target language and the output will be the speech in the target language. So the main function is to translate the text back into the spoken language using text-to-speech synthesis. So these systems are expected to generate spoken language that should sound natural. Okay, natural, not robotic. So it should be capable of maintaining the correct pronunciation and intonation and accent. I'll be talking about direct S2S translation systems later on. I'll be giving you some examples of direct S2S systems which are available today or where research is going on. So this is the second approach, which is the direct speech-to-speech translation, which uses sequence-to-sequence model. So deep learning technology is being used in the direct S2S translation system, where you don't need the intermediate text here. The input to such systems will be speech and the output also will be speech. So the system will be able to convert speech to speech without the intermediate transcription that is required in the traditional approach. So these systems are highly complex. They involve huge training data and they create embeddings from this large data sets of different languages and waveforms. Now coming to the classical approach, which consists of cascading the three main modules, that is the ASR module, the machine translation module, and the text-to-speech module. So in this diagram, you can see that this system is converting speech in Japanese, say for example, to speech in Hindi. So here you can see the first block is the ASR, which will convert the speech in Japanese to text in Japanese. And then you have a machine translation module, which is converting Japanese text to English text. And then another machine translation module, which is converting English text to Hindi text. And finally, the text-to-speech module, which will convert the Hindi text to Hindi speech. So we could have had a single machine translation module as well, which would have converted the text in Japanese to text in Hindi. But here we have used an intermediate language, that is the English, because for English, a lot of tools and technology is already available. So using such an intermediate language will be helping us in the translation process. Now, let me introduce you to the first module, that is the automatic speech recognition module or speech recognition module or speech to text module. Okay, so the main function of this module is to transform raw audio into a sequence of corresponding words. So what is the goal of the ASR? The goal of the ASR is to accurately and efficiently convert a speech signal into a text message transcription of the spoken words. Okay, so the point to keep in mind here is the process of recognition, speech recognition. This should be independent of the device which is used to record the data, speech data. That means the microphone that is used, the build of the microphone, the quality of the microphone. So it should be independent of this. Then the process should also be independent of speaker characteristics, that is age, gender, accent, etc. These should not be constraints to the ASR system. Then likewise, the acoustic environment, for example, the recording might have been carried out in a quiet office or in a quiet recording room, or maybe in a noisy room, or maybe outdoors, but it should not affect the output of the speech recognition system. So the ultimate goal is obviously to perform as well as a human listener role, but then it is far to be achieved. It has not yet been achieved. Now, the ASR problem, the problem that I mentioned now, that is the problem of transforming a spoken utterance into a sequence of tokens. And these tokens may be words, syllables, phonemes, characters, etc. So this problem depends on many factors. For example, it might depend on the microphone, the quality of the microphone that is used, or it might the source speech data that is being used, the speaker. For example, you might have speaker dependent systems or speaker independent systems. Then the language or the vocabulary that you are using to design or to train your ASR. So you might be using open vocabulary or closed vocabulary. Then the size of the vocabulary may be small or it may be very huge. And the type of speech that you are using to train, it may be read speech or it may be spontaneous speech. Similarly, the output of the system may be being the transcription, that is the text transcription, or the output of the ASR may also be speaker identity, or it might be keyword spotting. So the ASR may also be used to spot keywords in the input speech data. So some of the applications are speech understanding, language learning, spoken translation, audio information retrieval, virtual assistance, medical transcription, etc. Now, based on the ASR problems that I just mentioned, that the factors that I mentioned just now, you can see that there are different types of ASRs. For example, you can have a speaker-dependent system, you can have a speaker-dependent ASR system, or you can have a speaker-independent speaker system, or you can also have a speaker-adaptive system, where speaker-independent systems, you start with speaker-independent systems, and then the systems will have the capability to adapt the voice of the new speaker, provided you give a small amount of speech data of the new speaker. Then based on the nature of utterance also, you will have different types of ASR systems. For example, the utterance that you are providing, it may be isolated words. Okay, so in that case, we have an isolated word recognition system, or it can be connected words. So in that case, we'll have a connected word recognition system, or if the system is able to recognize sentences spoken continuously, we'll have a continuous speech recognition system. And then there's the most complex one is the spontaneous speech recognition system, where the system should be capable to handle speech disfluencies, grammatical errors, etc., which are present in the conversational speech. Because when we speak, there will be a lot of disfluencies, there will be a lot of grammatical mistakes also. So in spite of all those, the system should be able to give us the proper transcripts, should give us the proper output. So that will be the most complex type of ASR, which is the spontaneous speech recognition system. Again, the vocabulary size also may differ, because you might design your ASR for a limited domain. Maybe you are designing for a particular domain, say agriculture, or maybe for a religion. So in that case, the vocabulary size will be small and limited. Then another type of ASR will depend on the spectral bandwidth, that is whether it is the input speech that is used, whether it will be wideband or narrowband. Because if the speech that you are getting, if it is the output from a telephone or a mobile, then it is going to be band limited to the particular frequency, say around 300 to 3000 hertz. So in that case, it will attenuate the higher frequency components. And then this type of speech, that is narrowband speech, so obviously the ASR will also be restricted to only narrowband speech. And wideband speech is the one that we can directly record. So that is wideband, because it will be covering a wider spectrum of frequencies. Now, all of us, we have been recognizing speech very easily, and maybe from around 2 years or maybe 1 year, we have developed this capability of recognizing speech, isn't it? So how, as humans, how we do it? How do we do this recognition, speech recognition? How do we do it? So the speaker formulates the communication process, if you say. The speaker will formulate the idea in his mind, and then he will formulate it into words. So when he has formulated it into words, he will take into constraints of the language. He will say, okay, so I'm going to speak in this particular language. So he will use the grammatical rules of that language. And then using the different articulators, like the vocal cords, the tongue, etc., he will produce the required sounds. These sounds will be transmitted through the communication channel, which is the air, the medium is air, as an acoustic wave, and it will reach the listener's ear. From the ear, using auditory nerves, the messages will be sent to the brain, and the brain will convert these vibrations into a particular meaningful language or the content. It will the information. So this is how the recognition will be done in a human being. But in computers or in machine, that is machine is the computer. So how is it going to be done? Basically, the acoustic waveform that we are going to send, that is going to travel through the acoustic medium, that will be captured by the microphone, which is the sensor, and that the sensor, that is the microphone, will convert the acoustic waveform into electrical signals, and these electrical signals, digitization will be carried on, and acoustic analysis will be carried out, and then finally linguistic interpretation to tell you what exactly is the meaning of the acoustic waveform that you have captured. On the right hand side, you can see a figure here. If you look at the figure, you see here, you speak it through your device. So on the microphone, you speak it, for example, what's the weather forecast. Now, the device will create a waveform from the sound, that is, it will work as a sensor. The background noise will also be reduced and the volume is normalized. So this type of a basic pre-processing that will be carried out in the microphone sensor itself. And then the filtered waveform will be broken into phonemes. Each phoneme is like a link in a chain. So based on the first phoneme, statistical analysis is used to find the most likely phonemes to follow. For example, you see here on this right hand side, you see here, suppose you have the phoneme WH, that is say work. Okay, so you can see here the remaining phonemes, what are the phonemes that are going to follow. You see that there's a phoneme A, which is 32% likely, and then you have the probability of occurrence of ta is 71%. Then wa followed by a is 25%, and a followed by r, ra is 16%. So this way, the system is going to calculate the probability of occurrence of the remaining phonemes given the initial phoneme. And then it will take that path. So that path will be selected where the probability is maximum. Like for example, in this, you see here, wa followed by a followed by t, 25% and 71%. That is leading to the maximum probability. So the word formed will be what? Okay, so the word formed will be what? So this actually, later on we'll see, this actually is the job of the acoustic one. Okay. After that, once the words are formed, the words are connected in a meaningful way to form a sentence. So you can see here again, the word words will be followed by different words, and you calculate the probability of the different words following this particular initial word. And this will be done by the language model. This is the job of the language model. And you can see finally the sentence formed, the path that is taken. What's the weather forecast, right? So this path, you see the probabilities, you will see that if you add up, you'll see this is the path which has the maximum probabilities. So that is the sentence that is going to be formed, or that is the hypothesis sentence. That will be the output of the speech recognition system. I'll not talk about the history of this, but the initial, the earliest speech recognizer, if you see, it was a toy called Radio Rex. Radio Rex was actually a small dog which was housed inside a wooden kennel, a wooden house. And when the name of the dog was uttered, the dog would come out of the box. So the very basic idea was used, that is, the dog was operated using a spring, and that spring was released by an acoustic energy of approximately 500 hertz. Now it would look like when you are saying the word Rex, the dog comes out, but actually what was happening was, when you say Rex, the formant frequency, I talked about formants in the last lecture, the formant frequency corresponding, the first formant frequency in fact corresponding to the phoneme A in Rex. So that phoneme, that the formant frequency is approximately 500 hertz. Okay, and the spring that was used to operate this dog, that is this small toy, that was also operated by a frequency of 500 hertz. So basically what happened when you spoke the words, from the acoustic waveform, the formant, the energy that is extracted from this waveform, that was used to operate the spring, and the dog used to come out. Okay, so that was the first instance of speech recognition way back in 1920s. And after that, we had a number of other recognition systems like Audrey, Shoebox, Harpy, then Julie, Dragon Dictate, and so on. And ultimately, we have today deep neural network based systems such as Siri, Alexa, and Cortana, which you are more familiar with, the names of which you are more familiar with. Now, what we see is that although more than a century has passed, still we are not being able to achieve 100% accuracy, right? So what is so difficult about this process of speech recognition, which comes so naturally to us human beings? We have the physiology and anatomy to accept an acoustic wave, and it comes naturally to us. You don't have to think at all, isn't it? But for a machine, that is for a computer, it will have to convert the analog signal into a digital representation. So you need to, analog to digital conversion process needs to take place. Now, when someone speaks to us, we have to separate their words from all the background noise. So now, even while now I'm speaking, the sound of the fan is going on, so you might have heard the sound of the fan, but still you are able to recognize my words, whatever I'm saying, isn't it? But in case of the computer, you will have to do a lot of processing to separate the speech signals from the noisy background. Again, I may be speaking very fast, I may be speaking very slow, but then you know when I am starting a sentence, you know when I'm stopping, you are being able to segment whatever I'm saying quite naturally. But for machine, the machine will have to deal with endpoints in speech. So endpoint detection in speech is also a very important area. Again, whether it is a person, male or a female, whatever accent he's using, the style of speaking, the intent, the emotion, the age of the speaker, as a human being, we are able to understand what the person says. But for the machine, it will have to account for all such variabilities in speech. So whether you are talking, now when you're talking with a baby, suppose you're talking with a baby or a kid, you're going to talk in a different way, isn't it? You use certain words which are not at all meaningful, in fact, not at all meaningful. I'll just say like, one could take out the baby for a walk. In Assamese, we usually say fufu, and we understand that fufu means you're going to take the kid out for a walk, isn't it? So in spite of all these differences, we understand. As a human being, we understand, but definitely your machine will not be able to understand all these things. An elderly person, he might have problems, he might not have teeth, therefore his pronunciation will be difficult. But still, as a human being, we can understand what exactly he's trying to convey. But again, the machine will have a lot of difficulty in interpreting this type of speech. Another very important problem or another difficulty is disambiguating the homophones. For example, the word T-O, T-W-O, T-W-O, all of them, they have different spellings, different meanings, but they are pronounced identically. And the system will have to disambiguate between these different versions. Then there's another problem that is, I already mentioned, the disfluencies. So again, the machine will have to filter out all these fillers or disfluencies. And then there might be misunderstandings. For example, we may hear sentences incorrectly. Still, we will try to say, we can try to understand the meaning of this. But then the machine will have to find out different ways of understanding or managing these misunderstandings. And again, to add on top of all this is the syntax and semantics of the language. So all of this will make the speech recognition task all the more difficult. So the complex tasks which are involved are digitization, signal processing, phonetics and phonology, lexicology and syntax, syntax and pragmatics, and finally pragmatics, which means filtering out the dissonances. So you can see that a lot of complex tasks are involved in the speech recognition task, and some of the sources of variability. Now, I just go through it very quickly. The variability in speech sounds. This is one reason why all speech processing tasks become very difficult. Variability of speech sounds. Physiological, because each one of us will have a vocal tract of different length and area. The mass, vocal fold mass also will be speaker dependent. That is, it's going to vary from speaker to speaker. Then behavioral source, that is the syntax and semantics of a particular language will influence the prosodic pattern of an utterance. So again, the accent and the uses of words, that is the vocabulary that is used by the person, that will depend on the regional and social background of the speaker. So all these are again different sources of variability. Then environmental conditions, phonetic context, acoustics, because variability, there might be variability between speakers, that is inter-speaker variability or intra-speaker variability also. Now you will see that if you record your own voice, you will see that at different moments or maybe every time you speak, the speech signal will be slightly different. Now, let us delve into the ASR system. So this is the basic architecture of an ASR system, and these are the basic components. So we have the first thing will be the input speech signal, and then you need to find a representation, that is the digital representation from where you extract the relevant features, and then these features will be fed to the speech decoder. And the job of the decoder will be to search efficiently for the most optimal answer. So the most optimal string of or sequence of words. And the speech decoder will use information from the pronunciation model, from the acoustic model, from the language model, all of which will be trained from the speech data and text data, which we will be using for training. So this is another way of representing this speech recognition module. Actually, you can see here in this you will specifically see the acoustic module, the lexicon, the language module, and then you see the input speech from where you have extracted the features, that is the spectrogram, from where you have extracted the mel frequency capsular coefficients, which are fed to the decoder, and then finally the output of the decoder, which is a word sequence. Now this word sequence, it is that is W star, it is equal to argmax of probability of W given X, and this expression can be rearranged to give you argmax of probability of X given W multiplied by the probability of W, and I'll talk about this later. The probability of X given Y will come from the acoustic model, and the probability of W will come from the language model. So these two probabilities, which are outputs of the acoustic model and the language model, they will, that the product of that will finally give you the word sequence. So coming to the ASR now, the acoustic model. So as I have mentioned here, the first thing is, given a trained speech recognition model and a test speech signal, the goal of the system will be to hypothesize the best sentence, that is the best sequence of words. So if A represents the acoustic feature sequence extracted from the test data, so whatever data, the speech signal that you have given, you have extracted the feature, and A represents the feature sequence, then the speech recognition system should yield the optimal word sequence. Okay, word sequence WCAP. WCAP is the word sequence which matches A best. So that is why we say that WCAP is equal to argmax of probability of the word sequence W given the acoustic feature sequence A. Okay, so This can be rearranged and you can write this for that probability of W given A as probability of A given W multiplied by probability of W divided by probability of A. Okay. So in this expression, probability of A given W, that is actually the likelihood of the feature sequence A given the acoustic model of the word sequence W. Likewise, P of W, that is probability of W, is the probability of the word sequence. W is the word sequence here. So this probability of the word sequence, that is how likely is this particular word sequence. The probability of A given W is how likely this acoustic feature sequence given a particular word sequence. So that will come from the acoustic model. Okay, because the acoustic model is responsible for predicting the sequence of phonemes that would follow given a particular phoneme. Okay, so you are giving the features, acoustic features of a particular phoneme, then the acoustic model will predict the acoustic features of the next phoneme sequences that are likely to follow this particular phoneme. Then P of W is the probability of the word sequence. That is how likely is this particular word sequence. So that probability will be calculated by the language model. And P of A, that is probability of A is the acoustic feature sequence. So probability of the acoustic feature sequence, this is a priori probability. That means it is a priori means it is considered to be true without being based on any previous experience or any previous observation or something like that. So this is totally independent of the acoustic model or the language model. So finally, we can say that the probability of the word sequence, it can be approximated as the product of the probabilities of the acoustic model and the probability of the language model. So here you can see it is illustrated here. You can see the acoustic model here. Every phoneme that you will get an acoustic model for every phoneme, and then the pronunciation model or the lexicon. The lexicon will tell you exactly how a particular word is to be pronounced. For example, take the case of the word CAT. So should it be pronounced as cat or cat or sat? So that the exact pronunciation that will be given by the lexicon. For example, here you know that CAT should be pronounced as cat, right? And the last is the language model. So that will give you the probability of the word sequences. For example, here you can see the word cat followed by the word dog. The probability is given here. So same way the word cat followed by the word the. So the probability of that particular word sequence is given here. So that way the language model will give you the probability of the word sequences. Now I'll quickly take you through the acoustic model, language model, and the lexicon, that is the dictionary, or the lexicon, that is the pronunciation model. So the first is the acoustic model. The main responsibility of the acoustic model will be to recognize the acoustic patterns of speech and then forecast or predict which sound or phoneme is uttered. Okay, so basically, GMM or an HMM is used to model the acoustic model. So HMMs are most popularly used mainly because the hidden marker model is capable of modeling and matching sequences that have inherent variability in length as well as variability in acoustic characteristics. So this is the most preferred model, the HMMs. And the popularity of HMM is another reason is because of the existence of efficient algorithms for estimating the parameters, HMM parameters. And another advantage of it is HMM is its ability to integrate language models as well. So integrating language models together with an HMM based acoustic model. Now, language model again. So it was again now for acoustic models also you'll see that it is not just HMMs. Nowadays deep learning or end-to-end models are used for acoustic modeling also. Okay, so that same thing is happening in language models and for other models as well. So for language model now, coming to the language model, the main objective is that it should derive the best sentence hypothesis subject to the constraints of the language. So basically, two main categories of language models which are commonly used. One is the statistical model, which uses n-gram grammars. For example, you have say bigram model. A bigram model will predict, or it will tell you the probability of two words occurring together. Okay, so like I said, suppose cat is. So how likely it will that those two words will come together. So that way, n-grams or bigrams will tell you that. And then you have word transition network as well, which also will be used to predict the word sequence. So the next module in the ASR pipeline is the pronunciation or lexical module. So I already told you. So this is basically how it is going to tell you how exactly every grapheme is going to be pronounced. Okay, how the sound. So it's going to tell you how the phonemes are going to sound. Now, coming to the approaches which are used for designing ASR now. There are multiple approaches which are used. For example, we have template-based, where templates of words and phonemes are stored, and then whenever a particular speech signal comes, then it will try to match it with the particular template. So it will extract the features and then it will try to match it with a particular template. So basically, it is simply a similarity matching problem. So, but there are a lot of disadvantages, because if the templates are very similar, then it is very difficult to distinguish. And if the input differs slightly also from the template, then also the output of the system will differ. Then there are rule-based approaches where multiple rules, that is not many rules, in fact, where rules will be designed or rules will be used to convert speech to text. So here again, knowledge of phonetics and linguistics will be very essential to design a rule-based ASR, because for developing the rules for converting speech to text, knowledge of phonetics and linguistics is very important. So you have to use phonetics, you have to be well familiar with phonetics, phonology, phonotactics, syntax, pragmatics, etc., etc. Only then you will be able to design the rules to design such a system. But again, here also you will not get very good results, because it is not possible to express or design rules that will cover the entire vocabulary of the language. And then if a particular sentence falls out of a particular rule, then it will not be able to function, or it will not be able to give the correct output. Then another approach is the statistical approach. So in the statistical approach, again, a huge data, that is huge data will be used, and more powerful mathematical and statistical tools will be used to develop this type of an ASR. So mainly the statistical based ASR will try to train the system to learn the correspondences between the given speech and the corresponding text, and then it will be able to predict it. Now, coming to the drawbacks of the traditional approach of ASR again. So ASR, as you can see here in ASR, we have the different modules. That is the modules that I just mentioned, the linguistic model, the lexicon, then the language module. So this is the traditional approach of designing an ASR. So here again, there are a number of errors. One drawbacks. So one is the error propagation through the stages. So error will be accumulated. And secondly, there's another important one is each model needs to be trained independently. So you have to train the language model independently, you have to train the linguistic model independently, and this would require a lot of time and labor. Then again, the data has to be aligned. That is, the speech and text data has to be aligned, which will also require a lot of human effort. And then when you want to, expert knowledge is necessary to build custom phonetic sets. So the phonetic sets that are going to use the phonetic, because you have to build the phonetic dictionary. So you need expert knowledge from linguists as well, or from phoneticians as well, when you're going to design this this sort of ASR. So today we have end-to-end approach also, the end-to-end deep learning approach for designing the linguistic models. So here what will happen? in such, this system will directly map a sequence of input acoustic features into a sequence of graphemes or words. Okay, so this will not be relying on the acoustic models and language models and all, but it will directly convert from the speech to the corresponding text. Okay, so one of the most common approaches is the connectionist temporal classification (CTC) approach, which allows the system to learn to align the input with the output. The input being the speech and the output being the text. So here I am presenting a deep learning speech recognition system, architecture system, where you can see this is basically a system where the acoustic model is a neural acoustic model. Okay, so you have the input text, the preliminary feature extraction and feature pre-processing is being carried out here, and you extract the spectrogram, which is fed to the acoustic model. So the spectrogram is being fed to the neural acoustic model, and there are a number of neural acoustic models which are available, such as QuartzNet, CitriNet, ContextNet, Conformer, CTC, etc. These are cutting-edge neural acoustic models, and the output of this acoustic model, this the output, that is what is the output? The probability of the characters and words. So that is fed into the decoder along with the language model. So you have a decoder with the language model, and the output of the decoder will give you the corresponding text, which is devoid of any punctuation and capitalization. So in this particular pipeline, you see there's a punctuation and capitalization model as well, which will be responsible for putting the necessary punctuation marks and wherever necessary, putting capital letters and so on to give you finally the output transcript. Coming to the drawbacks again, end-to-end deep learning approach also will obviously have some drawbacks, and the most important is that the training data has to be abundant. So for low resource conditions, end-to-end models will not work very well because these models are very data hungry. For example, the Conformer 2 model at Assembly AI, which is a very popular model, which is a very recent model. This has been trained on around 1.1 million hours of raw audio and video training data for achieving industry best accuracy level. So you see the amount of data that is being used here for this end-to-end model. That is the Conformer 2 model at Assembly AI. Another drawback is flexibility in domain change. For example, if you want to change the domain, then it becomes slightly difficult for end-to-end systems. For the traditional approach, what happens is that you have the language models, the acoustic models, all these are separately designed, all these are separate. So then it is easier to adapt it to a new domain. But in case of end-to-end systems, this poses a problem. But obviously, ongoing research is being going on where external language models or acoustic models can be integrated into the end-to-end deep learning models as well. So these are some implementation tools for deep learning models: Mozilla Deep Speech, then you have Faldi, then NVIDIA Tau Toolkit, NVIDIA Riva, NVIDIA Nemo. I think one of the most popular one is Kaldi, which is an open source toolkit. This is used for developing speech recognition systems. Although it is it's not a very recent one, but you can use, I think, deep learning can also be incorporated into the Kaldi toolkit. So all the different steps of data preparation, feature extraction, training models, etc., can also be carried out using this Kaldi. So these are some data sets which are popularly used for speech recognition tasks. And now I move to the next module in the pipeline of speech-to-speech translation technology, that is machine translation. So basically, what will a machine translation system do? What will a machine translation system do? Machine translation system will mainly convert text in a source language to text in a target language. So the goal of machine translation is to produce translations that are not only grammatically correct, but they should also convey the meaning of the original content as accurately as possible. So some of the main approaches to machine translation, we have rule-based machine translation, which will be using a bilingual uh, dictionary. So using a set of linguistic rules for each language, you can develop a rule-based machine translation that is translating from speech in the source, text in the source language to text in the target language. And prompt and system are examples of rule-based machine translation systems. Then we have statistical machine translation, where instead of depending on linguistic rules, statistical machine translation will be using machine learning for text translation. So here the machine learning algorithms will examine the extensive human translations from this text to text, whatever translation is being carried out, and it will try to identify patterns, statistical patterns, and this will be used to develop the statistical machine SMT-based machine translation module. Then we have neural machine translation module, which will be using neural networks. And then we have hybrid machine translation, which will be incorporating multiple types of approaches to form the final machine translation. So here's an architecture of a statistical machine translation system. You can see here, you can see there's a morphological analyzer for the source language as well as a morphological analyzer for the target language. And this, on the left hand side, you see the morphological analyzer of the source language, which will be using the source language dictionary as well as the source language text, and then will produce the outputs, that is the tokens, you can say. And this will be fed to the source language parser. So let me go take you down to this particular system. So the job of the morphological analyzer will be to decompose the words into the constituent morphemes. And what are the morphemes? Morphemes are the smallest units of meaning that a word in a particular language can be divided into. Okay? So the main job of the morphological analyzer will be to give or output this small units, and which so the process will involve extracting the morphological parsers, so the root form, affixes, and morphological features of a given word, which is called the token. And the main functions will be morpheme segmentation. That means you will identify the prefixes, suffixes, etc., or the root words, and then segment it, and then come up with the morphological components. Then the next function will be identifying the lemma, that is the base form. Then POS tagging is another function that is part of speech tagging. It will try to assign the grammatical categories, and that a particular token will be assigned the particular part of speech, whether it is a noun, whether it is a verb. Then another function is generating the inflected forms. For example, the word find and the word found. Find and found both belong to the same root word find. Okay, so these are inflected words also. And then finally, integration with lexical resources. So the job of the morphological analyzer will also be to integrate with dictionaries and linguistic databases to enrich the analysis and improve the translation accuracy. So let's take an example. Say, for example, the sentence, she eats apples. So if you pass it through a morphological analyzer, the output of the morphological analyzer will be the word she, and what is the lemma for this she? Lemma also will be she only, and the part of speech will be pronoun. Similarly, for the next word eats, that is the next token, that is initially the tokenization will be done, that is the sentence will be broken into tokens. So this particular sentence has 3 tokens, she eats and apples. So the token eats, the lemma will be eat, and the part of speech is verb. Similarly, for the word or token apples, the lemma will be apple, and the part of speech will be noun. And finally, the full stop, that is the punctuation mark. The next in the diagram, in the architecture that you see, this outputs, that means all this, the lemma and all these things, the output will be passed to the source language parser. So what will this parser do? The parser, basically, the parser will, what will it do? It will analyze the grammatical structure of the sentences in a given language. So it will do a lot of different types of parsing. For example, the parsing may be syntactic parsing. Syntactic parsing again can be dependency parsing or constituency parsing. So in dependency parsing, it will identify the grammatical relationship between words in a sentence, and then it will try to find out which words are heads of a particular phrase, which words are dependent on a particular word, etc. So by doing this, it will try to find out the subject of the sentence or the object of the sentence, and whatever modifiers are there in the sentence. Then you have constituency parsing as well, which will analyze the hierarchical structure of the sentence to identify constituents of phrases and their internal structure. Then semantic parsing, which is optional. This will attempt to extract the meaning of the sentence. Then there are other functions as well, for example, syntactic ambiguity resolution, then normalization, then other syntactic and semantic information also. For example, other tasks, NLP tasks such as named entity recognition. Named entity recognition also, where every entity or every token will be given a particular named entity. And then sentiment analysis, text summarization, etc. etc. Now, approaches again, there are different approaches to designing a language parser. So we have again rule-based parsers, statistical parsers, neural network-based parsers. I'm just giving you a brief idea about what are the different technologies which are available for all the sub-technologies in speech-to-speech translation. So here is an example of a text-to-text translation system which is available online. The link is provided. Since I'll be sharing you the slides, you can refer to this link. This is an online translator where you can see that you can select the language and then give a particular source text. And then when you select the target language, the text in the source language will be converted to text in the target language. And in addition to that, this online translator will also provide you comparisons with the output of other machine translation systems as well. For example, at the bottom you see, in this example, you see the word, Assamese word Janmagata Bhabe has been converted to English, and the meaning is by birth. And then the same output, the output for the same word is given by the different translators. One is Crop or GROQ, then you have Microsoft, then you have Modern MT, then you have ChatGPT, and you have the Google Translator as well. So you can see the output which is given by all these different translators. So this technology, in fact, this system that has been designed, it uses 4 different machine translation systems like GPT-4, and it also uses GPT-4. So it will offer you precise translations that take into account the text context and nuances as well. So in this example, I've simply shown you a word, but then it will also be able to give you a translate a particular sentence as well by taking the context or the meaning of the sentence as well. So giving you a better, very good results. So this is the basic architecture of recurrent neural network-based machine translation system. So you can see here, you have 2 RNNs here. The first RNN which takes variable length sequences as input, and then it converts it into a fixed length vector. And then on the decoder side, you have another recurrent neural network which will convert the vector, that is the fixed length vector, into the it will convert the fixed length vector into the variable length sequence again at the output. So here's an example which translates, say, English languages to French languages, and you can see the 2 neural networks, one on the encoder side and one on the decoder side. So basically, this RNN uses an encoder-decoder architecture to translate text in English to text in French. So finally, we move on to the last module of the speech-to-speech translation system, that is the text to speech or the speech synthesis module. So speech synthesis or generating artificial speech from the text which is provided as input is performed in two main phases. The first phase is text analysis, which again consists of text normalization and pronunciation and analyzing the pronunciation. So text analysis, the job of text analysis will be to the input text will be transcribed into phonetic representation. And the second phase is generating the speech waveforms. So that means once the phonetic representation is given, that means once you have the phonetic sequence, then the next important function will be to generate the corresponding speech waveforms to produce the acoustic output. So coming to text analysis, a very important task in text analysis is text normalization. So text normalization, to sum up, this is the first task in all text-to-speech systems, and it is used to pre-process or normalize the input text in multiple ways. And I'll just give you an example, and you'll be able to understand what exactly text normalization is. Say, for example, you take the particular text for March 2014. So for March 2014. So if the input text is for March 2014, what should be the output of the TTS? Should it be for March 2014? No, it should be 4th of March 2014. Oh yeah, I need to say the text is for March 2014, right? Or it can be 2014 also, right? But the output of the system, text-to-speech system, should be 4th of March 2014. So that is one normalization that needs to be carried out. That means in case of, suppose, for dates and all, the date can be given in some form of number. For example, it may be given as, say, 04/03/2014. In that case, the output of the TTS system should not be 04 of the TTS system should not say 04/03/2014. It should say 4th of March 2014, isn't it? So, because when you're building the TTS system, there should be a mapping between the text and the speech. So, whatever text is given for the training text that is given, so that needs to be normalized, right? So that is why one normalization example that I've given you for dates. Another normalization may be for currencies. For example, when I'm saying $123, it should actually tell me, it should not tell me $123, but the output of the TTS should be $123 or $123, isn't it? So that way, different types of normalization have to be carried out. So again, here also, the text normalization system also can be designed using multiple approaches. So, and they can be dual-based approaches, neural network-based approaches, and hybrid systems as well. Another important task in text analysis is the G2P conversion algorithm, or the grapheme to phoneme conversion. So what exactly is the grapheme and what exactly is the phoneme? The smallest functional units of writing in any language, that is the grapheme. Okay, the text, that is the text characters, those are the graphemes. And the smallest units of sound that distinguish one word from another in a particular language, that is the phoneme. So basic units of sound, that is the phonemes, right? So G2P conversion is obviously required because the system is going to convert from, the TTS system is going to convert from text to speech. So every grapheme has to be converted to its corresponding phoneme. So G2P conversion is indispensable in various NLP applications, most notably TTS, ASR, and language learning tools. So here again, I'd like to mention that we have multiple approaches to design a G2P algorithm or a G2P conversion module. So it may be a rule-based, for example. Here's a very simple example. Suppose one phone may be associated with two letters, one phone, that means one particular sound. So for example, say for example, one sound which is associated with two letters, right? Say the sound K. K may be associated with C and K may be associated with K also, isn't it? So which means you will have to develop a rule for this particular mapping. And again, one letter may be associated with two phones. For example, the letter C, it may be associated with the phone Sir, it may be associated with the phone Ka as well. So that way, multiple rules may be used to design a grapheme to phoneme conversion model. Then you have statistical approach also. Then the first data-driven G2P algorithm was the net-talk algorithm, which was developed by Sanghamitra and Rosenberg. So LSTM model, which is particularly adapted to handling sequences, these are also used for grapheme to phoneme conversion tasks. Now, another important part of text analysis again, prosodic analysis. So by prosody, we mean those features which will make the sentence sound natural, not robotic, right? So earlier, if you remember, text-to-speech systems or speech synthesizers, the output used to be very robotic, but now you have very natural sounding output. So why? Because now the systems that are used for generating the speech, they take into account the prosody also. Okay, so the three main components of prosody, which are phrasing, that means how you produce a particular phrase, because normally when you have a phrase, the final vowel in a phrase will be usually longer than the previous vowels. Then, so this would often lead to a drop in the fundamental frequency or F naught, and from the start of a phrase to its end. So usually in a phrase, you will see that the fundamental frequency is falling towards the end of the phrase. Again, another important component of prosody is prominence. How prominent a particular word is, that is the stress or the strength which is associated with a particular word or syllable or phrase. And intonation again refers to the pattern of F naught variation over the entire utterance. So all these together will consist or comprise or compose the prosody, which needs to be captured and then translated to the output of the text-to-speech system. So various approaches, there are different types of speech synthesis like articulatory synthesis, formal synthesis, concatenative synthesis, unit selection synthesis, statistical synthesis, deep learning speech synthesis. I'll not go into the details of all these different types because most of these approaches are today not used, because articulatory synthesis, which models the articulators of the speech production systems, the output, the system is very complex to design, and the output also is not very good. Again, the formal synthesis, this type of synthesis uses formants, like I could mention the formants if you remember. So it will try to replicate the formants and produce sounds. Here also the sound is very robotic. Concatenative synthesis is, you can say it is a cut-paste sort of a thing, where you will be concatenating multiple segments or whatever segments are required. You will concatenate them to produce the required speech signal. And unit selection synthesis is also a type of concatenative synthesis, but the difference is that the output of unit selection synthesis is by far very, very good, because it is a corpus-based synthesis system which uses a huge corpus of speech units. So the speech units, again, selection of speech units is again another research topic in speech synthesis systems. That is whether you are going to, the unit is going to be a word, whether the unit is going to be a syllable or a phone or a diphone. So diphone based systems are also very popular. Gives very good results, because diphones usually what happens, what is a diphone? A diphone usually starts from the middle of a particular phone to the middle of another phone, the subsequent phone, and therefore the diphone is able to capture the co-articulation effect or the transition that is taking place from one phoneme to another. So that it is able to capture, and because of which it is a very good or very good unit, speech unit for speech synthesis. In the unit selection synthesis now, you will have all sorts of, you will have multiple units. So suppose it's a diphone, so if you will have all the diphones, or suppose you have syllables, Then you will have syllables in all sorts of context, right? That means it will be capturing different types of prosodic elements as well. So when you are using unit selection synthesis, there will be an algorithm which will select the best unit. Uh, yeah, unit selection. So basically, you will have multiple instances of each unit which will be stored in a unit inventory, and there will be a unit selection algorithm which will choose the unit that will best match the target specification. So this selection is based on two types of cost functions, that is the target cost and the join cost. And this technique was first introduced by Sagisaka et al. In ATR BTOX speech synthesis system. However, the disadvantage is building the database for this system, because this is a huge, you can say a Herculean task. In fact, it's a very time-consuming task, because you need to record the units in multiple scenarios. You have to consider all the prosody that may be possible, so that no prosodic modifications are required at the output. Then statistical speech synthesis. The advantages are lesser memory is required and more variations are allowable in this particular type of speech synthesis systems. Then we move to deep learning speech synthesis systems also. So here you have, today we have WaveNet, which is an audio generative model based on pixel CMM. This is capable of producing audio that's very similar to human voice. Then we have Tepotron, which is an end-to-end generative TTS model, which will synthesize speech directly from text and audio pairs. So this also has achieved a very high mean opinion score on US English. Then we have Deep Voice 1, and the architecture and all, everything is given in the slides. You can refer to the slides. So we don't have much time. So I'll just take you through this. So we have Deep Voice 2. Then we have another version of Deep Voice, that is Deep Voice 3. So which is using scaling text to speech with convolutional sequence learning. And then finally at the end, we, after going through all these different modules, so we will have to integrate all the different modules, that is the ASR, the TTS, the machine translation module, and the TTS module to build the final S2ST system. So finally, today we have end-to-end speech-to-speech translation models as well. So here again we have Translatotron. Translatotron has been developed by Google, and it is the first end-to-end model that can directly translate speech from one language into speech into another. So this is the first end-to-end speech-to-speech translation model which has been developed at Google. So initially the Google Translate has been using the traditional approach, that is the cascade approach, but now it is moving on to the end-to-end sequence models as well. So we have Translatotron, and we have other versions of Translatotron as well. We have Translatotron 2, we have the third version as well, Translatotron 3. So that brings us to the end of this presentation. So I'd like to put forward some research issues before you. So we have a number of research issues for you to work on. For example, the first challenge or issue, if you say, is the complexity of language, because language itself is very complex. It has intricate structures. It will have idiomatic expressions, cultural nuances, accents. So all the prosodic elements as well, which are very difficult to capture and translate in real time. Okay. Another issue is latency, because real-time translation will require time, and then it will not be able to provide you the translation in real time. So that is another issue. Then understanding the context is also very important. Sometimes if you translate direct from speech to speech, then without understanding the context or the meaning, then again your system might give you incorrect results. So context understanding is another very important issue. Then another issue is to, or challenge is to develop a robust speech-to-speech translation system. So robust in the sense this system should be able to cope up with all the disfluencies of spontaneous speech. For example, like the interruptions, then the fillers that we use in natural speech, the repetition, sometimes the false starts, all these things should be handled by the speech-to-speech system accurately. So robustness is another issue. And another issue is scalability and cross-domain portability. Because if you see most of the systems that are designed, these are highly domain dependent. So to reduce the complexity, most systems are designed to be domain independent. So if you want to port it to a different domain, so then that capacity or capability should also be there. So if you want to scale the data, then also the capability should be there for speech-to-speech translation systems. So that is another research issue. That brings us to the end of this. At this point of time, I'd like the purpose of this presentation, actually, the main purpose of my presentation was to familiarize you with all the different technologies that are involved in speech-to-speech translation systems. The technology which is used to develop speech-to-speech translation systems, like you see in the traditional cascade approach, you are using the automatic speech recognition system, you are using machine translation, you are using the text-to-speech system. Again, each of these modules will have sub-modules. Now, again, each of these sub-modules or modules can have different approaches to design, right? So whether you're using the cascade approach, which is considered to be the classical approach, or whether you are using end-to-end systems, which are the latest technology that is being used, the sequence-to-sequence models, the main idea is, what is the purpose of your design? What is the purpose of designing your speech-to-speech translation system? So that would help you choose between the different methodologies or approaches which are used to design the system. For example, suppose now we in our department, work is being done, research is being done in developing a speech-to-speech translation system for an endangered language, Northeast Indian language. Okay, so here the main intention or purpose of developing the speech-to-speech translation system is not just communication. Communication is obviously, no doubt, the communication is one purpose, to bridge the digital gap between the mainstream languages and this endangered language. That is one purpose, no doubt. But then another main intention or objective is to contribute different tools and technologies to this endangered language, because this particular endangered language that we have chosen is almost zero resource. So there are no resources. So our objective is to develop tools and technologies for this language. So what we do, so we have, that is the one reason why we have chosen the traditional approach, because in this approach, if we follow this approach, we will be developing different tools. For example, the ASR, the TTS, the machine translation module, all these will be developed in the process of developing the speech-to-speech system, speech-to-speech translation system. So these will all be separate contributions to the endangered language. But suppose we were not concerned about this. Suppose we were concerned about only building a speech-to-speech translation system for that endangered language, then maybe we would have opted for the latest technology that is using deep learning, using end-to-end systems, that is sequence-to-sequence models, where the input will be speech in that particular endangered language and the output will be speech in some other language, because then we do not have to design the intermediate technologies which are absent in that particular language, isn't it? So for that particular language, a low resource language, we do not have any other technology. So if the main goal is developing S2ST system, then we will opt for the latest technology. But since our objective is different, so we have opted for the other, that is the traditional approach. So that is why I'm saying when you are designing a particular speech-to-speech system, the main thing is like how you select the approach, what technology you are going to use to develop the system. That will depend on the objective, your goal. what is the purpose or intent for designing your speech-to-speech translation system. Okay, so that's all from my side. I know the presentation has been very long. Actually, the content is too diverse, too broad, and it is not possible to include everything in a single presentation, because every single technology that I'm talking about, that will need a separate presentation. But I've tried to intention was to give you everything, so that whenever you decide on choosing something, you decide to develop a particular system, you can decide what to use, because you know what is available. Okay. So if you have any questions, I think the students are all.
Yes. Any question from student sides? Any participant want to ask any questions? Bala, are you there? Isha? Ma'am, I have one question. Actually, we have done one work on multi-dialect Odia song lyrics corpus. Okay, that takes things, okay, not in the speech. So where we have implemented a binary linear support vector classifier using a form of representation of documents, I think bag of words strategy and TFI dev weighted skip. So actually that is there in the Odia song when so the corpus has prepared like this. Odia song is there and some Hindi word, there is code mixing and code switching. Those kinds of corpus we have collected. And we have implemented something there, this textual features we have find out and the hyperparameters we have. Those kind of work we have done. Okay. So can it be done in Assamese language or like that? And whenever we are going to take some speech or song, suppose Assamese song is there. So nowadays Hindi words are there in between in the modern song of Assamese or modern song of Odia. So by using some algorithm, we can identify those things during the speech-to-speech conversion. Like one song we are going to listen, and we have to find out which are the words which is not from Assamese or Akhomia. So
type of things can be done.
Have you done any work on this?
No, we have not done anything on this. But then definitely this can be done, because that is one technology that I would say is the language identification. So from the speech tokens itself, you will be able to identify the language, isn't it? Whether it is that particular
that can be done. During the lyrics, from the lyrics, we can find out the mixing words are, what are the mixing tokens are there. We have done that one is translation, like on text we have already implemented, but not in speech. So that can be done through this language identification only.
Yes, exactly. It can be done.
Okay, any questions from participant side?
Yes, sir.
Yes, Deep Shankar. Yeah.
So, ma'am, my question would be, if you are talking about some endangered language or low resource language, if the language is low resource in nature, then the dictionary will not be there. I mean, to translate from that language to the common language, dictionary have to be there because of the translation. So and the phoneme set also be not consistent because of that reason. So in that scenario, what will be the best approach? The deep learning approach or the standard approach? Which by which?
So, yeah, that is one thing, because the simplest way obviously will be the deep learning approach, because in that you simply have to collect the data. So data collection will be the most important thing. So if you simply collect the speech data, sufficient amount of speech data, and nowadays again pre-trained models are being used, isn't it? So up to some extent, if you can collect the speech data, and then your deep learning models can be used to convert it into the target speech. So in that scenario, I would say your end-to-end models would be a better option, because you do not have any other technology, isn't it? You do not have any other technology, like even if the dictionary is also not available, so you will have to build everything from scratch, isn't it? So in that scenario, I would definitely suggest you the deep learning approach. So for our situation, like for our condition, when I'm talking about the language that we chose, we had certain things to start upon, like we had the dictionary and all those things. So we opted for the traditional approach, and then and we are not mainly concentrating on the speech-to-speech system. We are concentrating on all the intermediate systems. So that is, so if your purpose is that, that means you want to develop different technologies for the endangered language, then you can go for the traditional approach. But otherwise, I would suggest the deep learning approach.
Is it clear, Dipsangan?
Yes, sir. So, ma'am, hello.
Yes, continue.
Yes, ma'am. So in that scenario, if the language, we can use some intermediary language as well. I mean, I have a language which is the dictionary is available. Suppose the language is Mizo and the Hindi dictionary is available. Mizo to Hindi dictionary we can find. So we can use Mizo to Hindi, then Hindi to English to implement the translation part.
Exactly. Yes, you're right. Absolutely. So because that is type of work is going on. So that is done mainly for all other technologies, whether it is the language model. Suppose you have the language model for Hindi and you do not have the language model for Marathi. You are working for Marathi, but Marathi and Hindi, they will have similar language nuances, isn't it? Similarly, the acoustic model, the sounds also will be quite similar. So you can definitely use an acoustic model or a language model of another language, similar language. But that you have to see, whatever you use, the similarity you'll have to check first. The language should be close enough. If the two languages are close enough, then definitely you can use the resources from the other language also. You can use an intermediary language also.
Ma'am, another question in the chat box. What is the difference between the acoustic wave and acoustic signal? Muhammad Ali has asked.
Acoustic wave and acoustic signal, I don't think it's different. It means one and the same actually. So acoustic wave also, we sometimes call it acoustic wave. We sometimes refer it as acoustic signal. So it means one and the same.
Ali, clear? Muhammad Ali, clear? What's the question?
You have questions, sir?
Yes, Bala, yeah. Waiting for you.
Okay. I just wanted to ask if we can be able to use user feedback from the native speakers to incorporate into the evaluation process to improve model accuracies and usability.
Didn't get your question properly. If you can include.
If I can be able to use like a user feedback from a native speaker to incorporate into the evaluation process to improve the model accuracies and usability.
That is another area where work is being going on. So basically you can have models which can incorporate the feedback into the system, and or there can be manual evaluation systems as well, where the output of the particular system can be evaluated by native speakers, and the feedback, whatever feedback is given, that can be incorporated in the model. So that is also possible. That definitely is being used to improve the accuracy or the output of the system.
Okay, so thank you, ma'am.
Okay, anyone, Isha, have you any questions?
So I want to ask another question.
Yes, Deepsan.
Sir, adding whatever sir added, that if nowadays some word we speak, yes, or the language we speak, it is not, we have used multiple words from other language as well. Suppose I am speaking Bengali, so I am using some Hindi words or some English words. So code switching is present. So to detect that in the ASR, we have to use some language derivation system as well, or no? That's
Use some language.
Language identification or the language derivation to identify the different languages.
Yes, that is done, because you have an extra module to identify the language. Just like you can use an encoder to encode the language, or you can use an maybe to identify the speaker also. So extra modules can be added. For example, sometimes you have tones, you have a tonal language. So in case of tonal language again, a normal ASR will not work because based on the tone of a particular tone, the meaning of the word is going to change. So in that case, you can incorporate a tone identifier or model to the ASR. So likewise, if you want to go for code switching, because most of the data, if you collect data in Assamese, suppose, you will have a lot of English words and Hindi words. So like I already mentioned to you, sir, right? That the identifying the language can be done there itself. From the speech signal itself, you can identify the language, whether that particular token belongs to that particular language or not. So that will be something extra that needs to be added to the speech recognizer.
Thank you, ma'am.
No questions are there. Thank you very much, ma'am.
Yes,
Okay,
thank you.
so-
Thank you everyone for bearing with me because the presentation was way too long, I suppose.
No.
Anyway,
They should know at least the keywords and what are the things that are available, and so that they can choose their topic and later contact us to start work. Okay, ma'am. Thank you very much. I'll talk you later, and you just decide the date so that accordingly you can.
sure, I'll let you know. Okay. Thank you
And
so much.
Bala has written, your presentation was excellent. Okay. So Bala is active in all the sessions. All
Thank
till now, all session. Bala, Isa, these are some people who are very active and interactive.
I'd like to ask you, what is the language you speak? Can I know the language you speak, Bala?
Bala, yes.
Yeah, I speak Hausa language.
You speak?
Yeah,
Hausa.
Hausa.
Hausa. Hausa.
Okay.
That is mostly in Chad also many people are speaking in Hausa. I am also translating one book in Hausa now. One of the book I am translating in Hausa language, and also some extractive summarization work, multimodal translation you can say we have done in Hausa also.
I love to work with other languages as well.
Yes,
so-
yes, ma'am. Definitely, as I told you, many of the countries of the Africa has joined here also. So that part I will take care. Always I'm say, talking about data, that part I will take care. And you are there to.
Because of time limit, I was not able to ask because I intended to ask the audience like what are the different languages you speak, just to get an idea. But so you must be knowing that since they are.
Yes, definitely, ma'am. I'll collect that one in a Google form, in the feedback form itself. And those who are interested, definitely we are collaboratively start a work. Thank you, ma'am.
Thank you so much.
Thank you, ma'am. Namaste, ma'am.